Levi, did you send your presentation to me?
Yeah.
I just got it. I'm like 2 weeks behind. Look, I got it right away. Well, I didn't know we.
Please resend once again.
Yeah.
Again?
To dmitry.kiven@gmail.com.
There's like paperback. Yeah.
Dmitry.killeen@gmail.com?
I thought it was cheese. It's just not prime. That we used to say. This was really good for that. Yeah. So what? Big trend. When is that? What is it? I don't know where, but I'm doing it this fall, and it's 1.5 kilometer swing. Okay. 28-mile bike. And it's a 10K biking swim actually. You ever swam that distance? No.
Hey, Javette.
I did a sprint 2 years ago.
Did you leave the lab yet?
No.
Oh, okay. Yeah, I didn't know that I was presenting until like I looked at my email like 20 minutes ago. So I didn't. Yeah. Are you over in the other room, other building already?
Just email.
Oh, okay. Can you run back over and print it? Run you back over to the lab and print out 12 chapters, I think. Dimitri said.
He's talking with German.
Yes.
Yeah. Okay. I think that's fine, unless Dimitri wants it written. But okay, sounds good. Okay, bye. Dimitri, it doesn't look like I'll have that meeting.
Okay. Javid, did you print? Thanks for Levi.
No, he just called me. Actually, I'm coming from class, so I didn't. Yeah. So you decided to.
Wait, what class are you taking?
No, I'm just attending. I'm not. I didn't register for.
Oh.
Which class?
That's a mathematical methods for physics.
So it's a 400, 600 level or 700?
Yes, 700 level. Yeah.
And it's Alan who's teaching it?
Alan, tell me.
We have everyone.
Zero camera. Oh yeah. Yes. I didn't. What is this app name you think?
This one from Levi.
Okay. So, Levi Lustrom will present as an employee of National Lab. He will present highly classified secret results, therefore they are not distributed in printed form. It's a good excuse for him. So, but you can write your comments on the pieces of paper.
Or just write them in an email.
I already, do you see your poster on the screen?
No, but I have it on my computer, so it's fine.
Okay. Good character.
Good to know. At least you have.
Should I start?
Yes.
So he's the first.
You are welcome
Okay.
to start and finish.
Are we having any limitation in time this time or no?
6, no more than
6.
20 minutes plus discussion for everyone.
Okay. So as you can see, my poster didn't really change that much, so I probably won't talk that long. I'll let you guys have more time for questions. The purpose behind this research is to figure out how core shell structures can decrease the rate of relaxation upon photoexcitation. And this work is done on a, you cut out your bulk crystal, 68 lead and 68 caucasianide. You replace the outer shell with the outer shell of lead with cadmium, and then you can make your core shell structure, which that is that's shown in both panel A and B in Figure 1, where the first one is we take out a eighth of the quantum dot to show depth, and then B is a cartoon representation. And we can see from the Figure 2, which is right below the ground state geometries, that the electronic properties are very similar. And this is good because then we can look into how different quantities change the relaxation. So one notable is the difference in mass from sulfur to selenium. Selenium is much heavier than sulfur, which means that sulfur can vibrate much faster, which could increase the non-adiabatic coupling terms, which go into the Tully's fewest surface switching algorithm for the non-adiabatic dynamics, which I will talk about in Figure 8. So taking the electronic structure, we can kind of generalize it into a quasi-type 2 quantum dot, which quasi-type 2 has the conduction band over the entire molecule, where the valence band is split onto certain regimes of the quantum dot, which is shown in Figure 2C. And what is noted, the colors in A, B, and C in Figure 2 show where I integrated the bands, and we can see that the bands are very similar when we exchange the caucasianide. And if we go past the molecular dynamics, because we talked about that a lot last time, and we go to Figure 8, which shows the non-adiabatic coupling terms, we can see that for lead sulfide, cadmium sulfide core shell structures, the nearest neighbor, which is, if we say our electron is on state HOMO +1, then our nearest neighbor would be HOMO -1, sorry. Then the nearest neighbor would be HOMO. And we see that in all cases, the black lines, which are for the sulfur, are higher than for the selenium. And this can directly speed up the relaxation, which, if we are trying to apply these quantum dots to solar cells, we would want to try and slow them down. So lead sulfide, cadmium sulfide would not be as ideal as lead selenide, cadmium selenide core shell structures, because the non-adiabatic coupling terms are higher, which drives the relaxation, which we can see in Table 2. The relaxation is anywhere between 1.5 to 2 times faster for the sulfur compared to selenium. And we fit this using a 4-state model, which is described in the methods section. And if you want me to go over the methods again, I will, but I figured we kind of talked about that last time, so I don't want to waste a bunch of time. And then from this, we can conclude that changing the chemical composition of the core shell structure, we can directly manipulate the non-adiabatic relaxation, which could be used to make quantum dots tailored for specific applications, such as solar cells, which then we'd want to use the cadmium solenoid lead solenoid cadmium wow, I totally messed that up. Let's say that's a bit slower. If we want to use these in solar cells, we could try and use lead solenoid, cadmium solenoid, which has a slower relaxation rate compared to the sulfide derivative, which could be very helpful in solar cell applications. And for future study, we could try and see if this trend is consistent with mass. So maybe lead telluride, cadmium telluride would even have a slower non-adiabatic relaxation rate, which then would make it even more suitable for solar cells. I think that's it. If there's questions, please ask.
Please join me in thanking Levi for being brief. Questions are very welcome.
So it's still unclear for me why, what is your reason for getting faster relaxation for sulfides rather than selenides? Yeah, you're saying that sulfides are lighter. That's the only reason.
Off the top of my head, the lighter element in my brain, if we look at equation 1 in methodology, where we get the non-adiabatic coupling, if the structure is vibrating more, then that will perturb the wave functions, and you can get an overlap that is greater when you do the time derivative, which in my brain...
This is not the proof, right? So you just speculate. There is nothing really in your equation showing that lighter or faster vibrations really should contribute to anywhere. Like your wave function doesn't depend on mass or anything. At least not in these formulas. So do you have really the proof for what you're saying? In other words, can you answer this question using your data, which you are showing on this poster?
What I think you're trying to ask is if we look at the simulated IR spectra, where we look at the interatomic distances and we look at how they change in time and then take a fast Fourier transformation, we can see that in the higher frequency from 100 to about 275, that for the sulfur compounds, which is the bottom panel in figure 4, we see that there is a shift in the vibrational frequencies that are important in the lead sulfide and cadmium sulfide, and you can also see the blue and black lines for solenoid. And if we look at the figure 9, the fast Fourier transformation of the autocorrelation function, in the regime where I was talking about, at about 200 wave number, we see a correlation in energies between the two figures, which means that the electron-phonon coupling between the cadmium, lead concatenide and cadmium concatenide help to relax the structure, because the FFT is showing some spectral density in that regime, which then which regime
you're thinking is the most important? So you're saying that this is a main difference which you see is around 200 wave numbers, from 100 to 200?
Yes.
This is the most important regime for making this difference?
The lower energy regimes, I think, come more from the vibration between metals, because if we look back at the figure 4, there is very little blue and black at low energy or low wave number compared to high frequency, which then if we look at figure 9, around 100 to 200, there are some bumps in the spectral density, which then could correlate to electron-phonon coupling.
Well, again, this is yes or maybe not, because if I'm looking on your figure 4, and this is again inserts which you really have to look on, right? Then
yes.
yeah, you have different range of energies, but in lead selenide it's more shifted towards 100. In lead sulfide it's more shifted towards 200. But overall, in both
yes.
cases, in these different frequencies, you have significant contributions of these vibrations, right? So
yes.
The only conclusion here is that you have your lead sulfide having frequencies 200, 250, while lead selenide having frequencies 100, I don't know, maybe 100 to 200. That's the only difference, right? But again, it's
yes.
unclear why this difference in frequencies, how this difference in frequencies should really affect the relaxation rates. How it's really, like, what exactly is the physical reason why low energy frequencies have low impact on your couplings comparing to the slightly higher frequencies?
I'm not saying that the low frequencies don't have an impact. I'm saying if we're looking at only the lead cacagenide or cadmium cacagenide, you don't really see that in low frequencies. You see more lead, cadmium, lead-cadmium frequencies. Where if we find the places where the cacagenide is important, that's higher in energy.
Well, I still don't see how this explains your faster relaxation.
Okay.
I don't see the you just saying it's like observation. Oh, look, for those which are relaxing slow, we have this. For those which are relaxing faster, we have that, and they are different. This is just some kind of, you find the correlation between the data, but it's still not answering the physics behind it, why, or what exactly this correlation does mean, right? So really think about seriously, it's the second time when I'm asking the same question and it looks like you're still not really answering it. You're on the right track, but you need to have a very solid idea for connecting this information and not just say, oh, here is just observation, right? There should be some physics behind it, which so far I don't see that you really can easily explain.
Yeah, and I'm not sure, unless the subgap in the PDOS in figure 2 at around -1 EV, if that plays a role.
Fig 2?
Figure 2A, where we're showing the projected density of state.
Okay.
And the reason why I point that out is when I tried to fit the population with a 3-state kinetic model, the fit was very, very poor. And I think that there are intermediate states that take some time to relax, and it may be that in lead sulfide, cadmium sulfide, that state is shorter lived, and it could be due to the higher vibrations. But that's also speculation, so I'm not sure.
I look on your 2B, figure 2B, panel top and bottom, they look very much identical. I don't see a big difference here between these.
No, I'm saying 2A, the subgap at -1 EV, that may be playing a role, but I'm not sure.
And again, just by energy, it's a little bit shifted, nothing else, right?
Yes.
Qualitatively, the structure looks very similar, just really the energetics a little bit different. then again it's unclear how this change in energy going a little bit to the red or a little bit to the blue, why it's really changing the relaxation rates. Okay, so please try to figure out this by yourself.
Okay. Any other questions?
Chance for questions 1. Chance for question 3. Chance for question 2. In reverse order. Thank you once again. I think I did a little error and printed wrong version of the next speaker poster. But so it's maybe previous one.
You printed the version of the speaker?
Yes, I printed a version of the speaker. But with the older version of poster, he may practice a new story or. So next speaker is Austin, and in addition to improving the presentation of materials in printing, it is very important that each of us practice how to explain it verbally and keep the strike of the visitors to posters. Do you need a copy for yourself as a reminder?
Sure. Take one. Just easier to look at. Thank you. All right, so starting off, this is actually the exact same poster as I showed last time as well. I haven't had too much time, and it's kind of been in the back of my head to update it. I've mainly been focusing on readings and getting a better understanding of DFT, ab initio calculations, and what they represent. So I'm going to try to go through that, spend most of my focus on today's talk just on the methodology and kind of relating the methodology to the two approaches that I'm going to try to take with this poster presentation. So again, this is the nuclear reorganization in manganese doped perovskite quantum dots, and the main purpose behind this is that perovskite quantum dots are already being used in multiple applications due to their light emitting and light absorption patterns that they have. The qualities with them are really beneficial to some electronics, solar cells, etc. So that's why they're really interesting and good to look at for future references and future things to go into. The problem with them too is that, however, they're continuously unstable in this factor. And the concept behind this research is that through the doping process, by replacing lead with manganese, that hopefully they could become, or the hypothesis would be that they would become more stable in the same respect that they've seen with other doping processes, that they may lose some of their ability of photoluminescence and actually quantum yield of how well these quantum dots work and continue with their light emitting and absorbing processes. So that's kind of the abstract and purpose behind why we're doing this research, what we're looking for, and again, you're just restating that hypothesis, seeing that if the doping process with manganese is going to create a more stable with some of the same outcomes of photoluminescence and quantum yield. So moving on from that, the main methodology that we'll be using, and this is all through really computational software, but the theory behind it, and again I plan on adding the formulas here and everything, is mainly density functional theory as well as ab initio calculations, and how those kind of go hand in hand, and I'll jump back and forth kind of between the methodology and the results here as well. So in the first results section, what that process was using MATLAB software was actually making just estimations on at what distances apart and energies that these quantum dots are going to be most stable at. So as the first table there kind of shows, it's just an approximation of running a bunch of values through the MATLAB software and the Wavelength program on what is going to be, in theory, the most stable structure and energies for these quantum dots. And around there you see, again, just kind of an optimization. I believe it's around, let's see, like the 75 to 100 it might be atomic units in there, range. And what that really means, going back to the methodology, with that is that we can use that for a starting point to actually calculate our ab initio calculations, and through that figure out if these energies are present at what level, then what are the best coordinates that the quantum dots and the structures can actually be placed in. And that goes a lot too, and what I plan on adding in, I believe the abstract section in the future, is the actually like optimization process as well, so building a quantum dot through software as well, so I plan on adding that into the abstract. But then through that, we can get this new energy and also new position of molecules, I guess you could say, or structure of molecules, and start applying that to the density functional theory, and starting off with those values of what the most stable configuration is, actually creating new energy from creating a new energy from that and plugging it into the ab initio calculation results. And from that, and those are kind of what the R and the E's in the results section, or the ab initio results section, contain. And those are just, you know, taking one calculation of what offset of, you know, things like metal to metal transitions or metal to ligand transitions for electrons are going to be placed. Sorry, a little unorganized. Going back to the results section, the estimated results section, what I did with that too is just, it would be essentially the same as the same metal to same metal transition in their ground states. That means that they're not offset in any way. They're the same molecule. They're the same, you know, form and everything like that. The bonds and everything really aren't offset from each other. So that's the kind of basis and starting point for seeing how electron transfer is working between that ground state molecule in the metal to metal. And then going from that, again, just jumping back into the ab initio results, and what we're looking for there is what happens when we start offsetting them and we start having these metal to metal transitions, these metal to ligand transitions, etc. And by taking those different energies and optimal positions that we calculated through the density functional theory, as well as previous ab initio calculations, and just optimizing them with each new result, seeing again how stabilized that molecule can become, or that quantum dot can become, therefore hopefully improving the stability of the entire molecule, and then also finding, again, I'm still kind of reading up on this part here, but actually making a definitive result of what happens to the photoluminescence and the quantum yield of it. So in this paper that I see is printed out, it doesn't have conclusions or references or anything like that, but the conclusions we hope to derive from this in partnership with Aaron Ford is, what are these, you know, what's the kind of trend that we're seeing with these doping processes of transition metals, and this one specifically with manganese. What happens to stability? In this example, we're placing it right in the middle of the quantum dot. But then in future references too, as Dr. Killen and I have actually talked about, is just finding different arrangements for the quantum dot and the perovskite cells. What happens if there's two molecules that are doped in the quantum dot? What happens if there's, you know, doping processes that are on the outer sphere of the quantum dot? What happens if you know, kind of mess around with the geometries based on that? So that's really kind of what we're looking for in the conclusions, and then also where the research kind of lies in the future. So that's kind of a summary of that. Hopefully it was maybe a little more educational for the people from the last presentation, but I'll be happy to take any suggestions and questions.
Okay, then thank Austin. So, questions and comments?
I have just very simple question. So
Yeah.
you have on your middle panel, you have a table.
Yep.
Why do you showing it to us? What exactly I don't think you even referred to it when you were discussing.
Yes.
Why you put it there?
So I tried to, you're talking about the table, not the figures, correct?
Well, it's table,
Both.
I guess they connected, right?
Right, they're connected. Yeah. So the table there, and I guess I did skip over a lot of it. The main thing with the table is just kind of seeing an optimization pattern for what we might expect the quantum dot to have, and that optimization follows things with like rate of reaction, or not rate of reaction, but rate of electron transfer, and that is good indication of what the stability of the molecule or the quantum dot might be like. So that's why it's included in there, and again, that's just estimated. It's plugging in values to see what the best value to start out for the actual ab initio calculation should be.
So then, how should I read it? What is your best result based on this table?
I thought I mentioned this briefly. Maybe it didn't make sense, so I mentioned it, but
I just want to connect it to your data, right?
yep.
My problem right now listening to you is that you kind of say, here is what we're going to do. So here are some results, this is our goal, right? But I still don't understand how exactly your results support any of your statements and how they're really connected with the things which you are showing on your poster.
I think
So
maybe.
even if you told it already, right?
Yep.
If there is a question, it means you're not really connected to, so people don't understand this connection. Right?
Sure.
So you're saying, well, this data you estimate from your results and it's showing the best conditions for your reaction.
Right. And
So
just
my question is simple. Which of these lines showing really the best conditions? So how exactly it's relate, like how do you make this conclusion? Which of them is really the best? Is it possible to get from your table?
yeah. I do not quite remember.
Then which
the
line to
results on
look
there. I believed it was when the initial momentum or energy setup on that system was 100 atomic units.
So I need to look on your first column with the number 100.
Right. So maybe just
And
high.
this provides the largest percent 68, but you have 72 in another line, right? Then
Right, but I
what
think it
exactly
also-
making me to think that this is the best?
Are you talking about your rate or your yield being your best?
I think rate of reaction is what I was going for. And again, I
I
don't
need to
remember
look
the
then on the
results.
rate, it's your last column, to see which of these guys gives me the largest one, and this is 9 something for this 100. So this is your best conditions. So it's not yield, it's a rate, which is your main factor.
Right. Yep, that's what I figured from.
And
And
this is the data for this table. They are from your simple model, or where you just playing with potentials, or this is based on the exactly potentials which you estimate from DFT calculations.
yep.
Yeah.
I mean,
To which part?
to which part? So,
Did you use Aaron's stuff or did you simplify it down?
well, currently I've only used Aaron's stuff, but basically the idea
Oh, so
behind
this
it.
table showing only when you're using your parameters based on the DFT calculations.
Right, and I haven't ran the process yet of, again, what I've understood from it is that by using, let's say, the best approximation that is estimated, I should be plugging that into the AB initial calculations, which I haven't done yet, to get my own results on what does that AB initial calculation look like. And I get what you're saying, I completely agree. I think I need to highlight more
It's
what.
not about what you got, it's about how you present it, right?
Yep.
You probably, when you discuss it with people who come to your poster, right?
Mhm.
Really, if they really have 10, 15 minutes, no one will be sitting with you for an hour.
Oh, yeah.
right?
It's very optimistic.
Yeah, I
30
feel-
seconds. If you do not catch attention, then okay, thank you.
Maybe-
Yeah.
Well, I hope at least people will stay for a couple of minutes at least, right? And if you start talking with them, they probably will not stop you after first second and say, oh, okay, whatever.
Sure.
So you probably will have at least a second. Think about maybe 10, 15 minutes, but you probably.
Right, and one thing I was gonna say too, just quickly in response to what you're saying about the estimated results, I think I might be approaching that wrong by saying it's a results section when really it's more of a preliminary step section
It's the
to
results.
see
It's preliminary results or whatever. It's results, right? This is what you got. And then the question is how you interpret it or how you can improve it
Sure, but again,
for your future work.
from my understanding, it seems like almost the AV initial calculations are going to be more pertinent and essential to making conclusions for this report. So I might include.
No?
No, you wouldn't agree?
No.
Oh, okay.
You may want to.
I would include everything in here, but just maybe read.
There is no space for everything.
Mm-hmm.
You already know enough information to fill all walls in this room, but the poster doesn't give this format. Your idea about ab initio being superior to your results is wrong. Your results in the central column with this zigzag snakes are superior to compared to ab initio. Ab initio is results is humble servant of your high-level wave packet calculations.
Okay.
You parameterize wave packet calculations with ab initio results,
You use
or with your educated guess. But quantized nuclear wave function is most challenging and impressive act that you can brag in public and people will respect it. So you show dynamics of quantized nuclear wave packet. Your dynamics of nuclei are not classical point charges, but wave packets. It is very impressive. When conference starts, you will not see much presenters at this high level because there are a lot of objective challenges, and you shouldn't brag your strengths. I'm not sharp today.
Wasn't planning on it.
You shouldn't hide your strengths.
Hide strengths. I was gonna say wasn't planning on bragging really in any fashion, but.
And also, just, again, for me, I don't understand, you have your green, and this is what you are showing, how you get these potentials and all these parameters from DFT calculations, right? The green, your very right green picture, right?
Right, and maybe I've been.
And then you have another one, or maybe it's an old version.
Yeah, this is still the old
So
version.
it's just a duplicate, right?
Yep, and I still do have all your notes.
That's why you took it out, because I thought they should be different at some point. Okay, so it's exactly the same thing.
Yeah. Like I said, this has kind of been in the back of my mind for.
And then again, these numbers with RG, RG, RE, right? So
Yeah.
you still have them.
Mm-hmm.
So what exactly they represent?
So from our conversation 2 weeks ago,
And you can point by finger on the diagram.
Yeah, sure.
On this green diagram.
So
RG, RE.
right.
From the diagrams, there's no any RG or RE.
But they should be there.
So again, correct me if I'm wrong, but what I've understood is E is really just like this energy offset that we're seeing between these two like metal to metal or metal to ligand electron transfers that can take place. And then I'm not sure if this is R really, but just the offset that's kind of more horizontal or on the x-axis is the distances that are actually between the bonds, which is going to be changing between the different types of bonding structures, again, the metal to metal, metal to ligand. So that's what the R and E represent and are kind of being played around with in the geometry of the quantum dot.
But then it looks like if each of this data which is showing on this table are already in your green figure,
Yeah.
what's the reason to duplicate it again?
Yeah, there might not be a reason. It was just kind of adding space to the poster for the first
But I
presentation.
thought you have
so.
more data rather.
Yeah,
I thought you had
there's-
the opposite problem, to hit all your data to the poster rather than really fill the space in the poster.
Right, and that might be it right now with what Aaron has going on as well. I still.
And you're out of conclusion, so I would suggest you probably can take this for conclusion part rather than this redundant information, right?
What part?
I mean, at the bottom where you have this table with data, which is just duplicating your data on a green, red colored things. pretty
Sure,
much the same
I
thing,
agree.
right?
I agree. I don't like
probably
if I can
can-
explain it myself. I don't think it's really.
Yeah, you don't really need a table because table is more confusing.
Yep.
Because the first question, what does this table mean? And then you go back to your figure and you kind of just repeat it twice, right? Explain it twice. Maybe if you really will have a space, it would be a nice space to put your, first of all, you out of acknowledgements and you out of conclusion sections.
Yep.
Use it,
still,
and it would be really appropriate way to put it at the end of the poster.
Yep. Still things to set up. Jabed.
I have a question.
Okay. I don't know. He's had his hand up for a while, so I think I'm gonna go.
Oh, never mind. I can't see anyone except you.
Oh, okay. Gotcha.
This is not a question actually. I'm just wondering in the last line of the table 2 leveling, you're saying the more specific and precise system energy. What does that mean?
I'm sorry. Could you say that one more time? It's
Very last line
table
of the
2.
poster is they use more specific and precise system energy.
I see what you're talking about.
In the caption of the table 2.
Mm-hmm. I think it may have just been 2 a.m. writing that I put down for the figure.
Okay.
So it's I don't know. From my understanding, it was my at that time understanding of exactly what I just answered to Dr. Kalina. Is just what that offset and what that kind of distances between the different bonds mean. So obviously needs to be reworded. Levi?
Okay. Does anyone else have a question?
We may have in the future.
So my question to you is, it sounds like you only have 2 geometries to make your surfaces. Is that correct?
2 geometries to make my surfaces. I would maybe even argue only 1, just
No,
because.
he's talking about the points, right? You
The
do
green.
points on a
Oh,
green curve.
right,
or
sure.
the black curves.
Yep, I'd agree with that.
But what is your question?
Why did you? What?
What is your question?
So my question is, why did you not do like an inner reaction coordinate scan from one potential minima to the other minima, and then you could get all of the energies between those 2 points, so you would not have to rely on parameterizing your 2 states using 4 points and assuming that you have a hyperbolic shape.
So, if I understand the question, which I don't entirely, but I'm going to try to answer it. Following the same concept of kind of what I talked about, and it's in my methodology. I didn't touch on it too much, but is the concept of Marcus theory, and that again, I don't necessarily know why it dictates that the 2 surfaces that you're analyzing have these kind of hyperbolic shapes to them, and that's where the parabolic, yeah. Shapes to them, and that's the theory that I'm going off of, and I was going off of with my presentation last semester as well. I guess you're asking why. So you said minima.
Tell them.
Yeah, because I'm assuming you optimize 2 geometries.
Okay. I've been told by some esteemed colleagues that these are single point calculations in BAS and not, multi-variable on Gauss view or anything like that. Gaussian.
Gauss view is just
So in theory you could, but you don't see a need.
Well, if we're only measuring between, okay, so Levi, if you can still see me, if we have an example like this, which is the quantum dot or the doping process that I'm talking about, if it's only between 2 molecules, there's really no need to have more than 2 surfaces of electron transfer that I'm measuring.
I'm not saying that you'll get more, but I'm saying you would not need to parameterize your 2 surfaces by taking 4 points and getting.
So are you suggesting
surfaces out of
taking
it.
4 points, or that's what I'm confused on?
Yes.
No, I'm saying that if you had geometries that connect well 1 and well 2, then you would just need to look at how much whatever theory you're in. So if you're looking at independent particle, then you could look at like your homo-lumo gap, right? And then you would have a smooth curve taken directly from ab initio calculations versus taking 4 points and getting 2 surfaces.
But Levi, in his calculations, it's actually one of the approximations that the curve has to be parabolic, right? So
Okay.
from this point of view, if DFT doesn't provide the parabolic shape, right, it has to be approximated to parabolic, because then his methodology, the results which he getting from his wave packet dynamics will not really work, because then it changes the shape of the potential. And his results obtained for parabolic potential, right?
Yes and no. The method of wave packet propagation will work for any potential.
But in his case, he was using parabolic.
Yes, and following suggestion of Levi to get more precise ab initio data for potential energy surface is good and correct, but it is not primary goal. There are much more important things.
Yeah, it can be stated as a future kind of future direction to maybe check that really from DFT calculations you can get the shape parabolic, or it will be not very much different from a parabolic. And then of course, you, as Levi said, you need these intermediate steps, not just 2 points, but you need to have many points to really see what exactly the curve is, right?
Yeah.
And maybe really prove that this is parabolic,
Right.
or maybe you really see something more complicated potential, some complicated function, right? And then again, you probably, as a next step, it means you have to modify your function for the potential in your
To actually fit
wave
that.
dynamics, right, in your actual code,
Yeah.
and then maybe get some better results.
Yeah, that'd be really interesting
But
to
this
see.
would be future, right?
Yeah.
Because you're definitely not getting it. But again, this empty spot, you can put conclusions, and then you can put future direction, and then go 1, get more points
That-
for potential for checking blah blah blah. Second, something else, right?
Yeah, that'd be a really interesting area.
I have a comment. No. Comment, because it is so many interesting discussions. Levi?
Yes.
So Levi wants to identify set of geometries in between these points and find more ab initio data for this interval of potential energy surface. Yes, this would be cool, but it is little addition to the overall picture which needs to be described. Those are only ground and first excited state. In the optical excitation, there are much more excited states which need to be taken into account. And if Austin does have energy and time to explore the system with again and again, it is better to do this relatively simple and quick calculation for more and more excited states and do quantum dynamics for either different pairs of excited states or many electronic states, each of which has some minimalistic description of the nuclear wave function. Levi, are you satisfied?
Yeah.
Okay. More questions to Austin? If no, then thank him once again. And please recall that there are 2 goals of our meeting. Goal of reviewers, of attendees, to criticize presenter, specifically in writing. Goal of author, to collect this feedback and implement it, hopefully immediately or maybe with little delay, so that next time, or for some of us next time will be already on the conference, there will be change. So the written comments are not for the space or for release the steam. It is help to author to improve the poster or oral presentation. So the next presenter is Christian Nieder. Please start, and I will distribute your.
Sounds good. So, obviously I have done some remodeling of mine this time. This is still very much a draft. I'm talking to you, Levi, on that one. So On the next one, so let's start off. I did not change much about my intro. I hadn't gotten to that, but as I discussed before, we were dealing with perovskites, which I have discussed before. It has to be in the structure of calcium titanium oxide. You can change out the molecules, but as long as it stays within that same structure framework, it's called as a perovskite. So in my first figure, I am showing my models of this of my systems. To start off with, I have two organic dyes. One's an unfunctionalized tribenzylamine, and then the second one is a functionalized tribenzylamine with hydroxyl groups added to it. C and D are just showing that in a more of a Gauss view look. And then right below that is the combinations with the organic dye to my system through a phys absorption as shown in C. And then with the functionalized one, which is the chemical bond between the hydroxide and the perovskite, which would be a hydrogen bonding. In E and F, I am showing that how the system will be working, and I'm showing that how when we excite that perovskite with light, we move a hole goes to the dye, which is an electron going towards it, and that's the excitation that will run a photovoltaic cell. So in E is just showing that there's a possibility of traveling through space or as in the phys absorption, and then we show it doing the same thing but through bond, and we're hoping to see how the rates change with the different scenarios of the two. I have discussed the methods section with Aaron. I just need to add some, but I need to discuss the process of which we gain the curvatures of my models, and these models are the top one is my model of the chemical bond, and the bottom one is my model of the through space bond. I made some assumptions. One, we made this assumption that the curvature of both the ground and the excited state are equal to each other. So on the right is our excited state system, and on the left, then the lighter green color is our ground state, and we're following the wave packet as it travels to it. The reason we are saying that the curvature should be the same is due to some, if you're dealing with heavy metals, you don't see much change in the geometry of it. That's what I've gotten so far about it. But you can see that the activations barriers are different between the two due to the distance of which they're spaced from with each other. So I want to discuss how I got those curvatures, and then I wanted to discuss equation behind our Arrhenius plots, and then just transmission probability, how we got our yields of the system. So to move on to our results and discussion, we changed the kinetic energy of our system, and that is what we're varying to see how with the more kinetic energy or less kinetic energy, and see how the rate and the yield changes as we of the systems. So to start, I looked at the through space model. As you can see, this is the figure 2B is where I the through space model. So I put the different kinetic energies. I'm planning to convert those into temperatures for an easier look for our people, just to see it as a temperature, not kinetic energy. And as you can see, as I increase the kinetic energy from the lowest point where I made it so that it couldn't transfer at 0% yield, and I increased it as we went. It very quickly, I got my optimal yield of 44% at a very low kinetic energy compared to the higher ones, because as soon as I got higher up, then there was most likely I had too much energy, and it started moving back towards the excited state from the ground state relaxation. The rate doesn't increase with the up to that highest yield, and then it will start decreasing a little bit again, as you can see. Through bond model is the exact same process, except it took more initial kinetic energy to get up, or not more, less kinetic energy, because we have less to get over, because the bond lowers our activation barrier, so we don't need nearly as much energy to get a higher yield and to get better rates. So that's what I'm showing in this table there. In table 2, I'm just showing that I did not quantitatively figure out the activation barrier heights. but based off my graphs, I just gave a good estimate upon where the activation barrier's energy is. I also showed where the starting position of where my excited state parabola is, because the ground state we set to 0, so it's just easier just to show where that is started from. And that just shows how much closer the bond scenario is compared to the through space scenario. Move on to my figure 2. We have I made a Arrhenius plot, and we're looking at how the temperature changes with the rate. So the equation would be the exponent to 1 over t is a simplified way of looking at it, and that is why my curves increase but then start to level off as we got to higher energy. So the circle dots and the blue line are my through space model, as you can, and then the triangles in the pinkish orange color is my chemical bonds. You can see that the through space model increases rapidly with a rate because it doesn't start off with any because there's no yield, and then it starts to taper off about the same point as with the through chemical bond. It's just that it takes less energy to have a higher rate with the chemical bond than it is with the through space model. So next is I'm showing the probability distribution of the wave packet in my system. So the wave packet is the blue parabola in here, and that in the first model is I'm showing the through space model in these two figures. The first one is where there is absolutely no yield. There is not enough energy to get over that activation barrier. So you can see that the wave packet just oscillates back and forth in that excited state. While when we move and give it enough energy to get over that activation barrier, you start to see that there's a second parabola that shows, and that is the ability for the wave packet to go down to the excited state. And that's just that is the show be able to get the yield and other stuff. I did not get to my conclusion. I did realize the first time I did these calculations, I had the wrong scenarios to the numbers I had, as you might have realized if you were here last time. My through space model was my through bond model, and my through bond model was my through space model. Don't know how that happened, but so my conclusions are a little off. Just think of them in terms of instead of the through space, it's the through bond that is that has the faster, better yield and the faster rates as observed. And that is about it.
Okay, let's thank Christian.
Any questions?
Yes. Any questions? I do have two questions which are general. I will not repeat them, but they are to anyone after each poster. So, and these two questions will be asked by visitors. Mm-hmm. First, I will ask two, and then you can answer two.
Okay.
So, first, what is your main result? And second, which equation allowed you to compute this main result?
Okay. So, I believe the main result is the rate I observed, and the
point.
These rate numbers right here, I would say would be my main result of basing off this, and these Arrhenius figures based off these results I got here. This figure is just a graphical representation of my table. I believe that is the main result because we were wanting to see how the rate of which we see the relaxation from this excited state down to the ground state, because this will then show how if the solar cell works well and if a recombination occurs, if I'm correct.
Okay.
The main equation to get this stuff.
It's absent.
Yeah, I know it's absent.
Don't hesitate. You know this equation,
What?
which allows you to get rate. You have already presented it as a part of the course.
What?
Previous course. Again.
Yeah.
How do you convert your green
well, your old poster is green. Green figure on the bottom into the rate. And some of you do quote part of the code in the posters. No, nobody will read codes. Equations are designed for better visual perception. They're nicer. They use calligraphic symbols rather than boring coding.
Well, the main equation we used the last semester would be Schrodinger's equation, but I know that's
No.
fully
Schrodinger's
correct.
equation is it is correct answer for everything. We
Yeah,
also-
yeah, I know. Trust me. It deals whatever they get our wave packet that do that equation.
And then you get population in each of the potential energy surface. So which is just a line that goes exponentially or with some oscillations. How you convert one line into one number?
I can't remember
One
off the
line
top of my
into
head.
one number.
Yes.
You just take a point from a line and this
It is formally correct. But you need a number that would represent the rate. If the line changes quick, then the number will be big. If the line doesn't change and change slow, the number will be small. So you need the rate.
Yes.
How do you define the rate?
Oh,
Huh?
I'm trying to help you.
Yeah.
I'm showing the slope.
What if the rate changes
What-
with time?
are we just
Then the question is more complicated.
get
errors.
with tangent? I mean, we're the
Slope,
tangent, the
slope,
slope.
slope.
Oh, that's just it.
So slope is
Definition
The-
from mathematics.
The slope would be the rate. What?
yes, slope is a rate. Rate is a slope. But but in calculus,
What's the slope of a linear line?
What, the y equals mx plus b? With the
Okay.
It can be.
How do you convert
This
that
is
to the
equation of
slope
line.
mathematically?
Levi, please wait just a second. If it is not a straight line, if it is something more complicated,
like
continuous line.
a continuous line.
Yes.
Uh,
And you took calculus.
yeah, I did. Doesn't mean I was.
So connect this. Continuous line and calculus.
How
First,
can you,
integration.
how can you find out the slope?
integration, okay, and what else?
in some nations.
No. Which other operation do you have?
Opposite of integral.
Opposite to integration.
Oh, a differential.
Yes. A derivative.
Yeah,
A
derivative.
derivative is a slope,
Okay.
right?
Yes.
So
yes.
this is the simplest equation that gives you the rate.
Okay.
There are more advanced things, but you want to put it in a box like dp over dt. Here's my main equation.
Okay.
And then it will make you very easy to address this question. Like, what is your main equation? Here's my main equation. And then
Your main equation is equation of motion, right?
Yeah.
For electron in this specific potential, right?
Yes.
And then you need to put these words into the mathematics. And he given you a hint that you need to start with derivative of what? Either you interested in coordinate or velocity or momentum, right? Equals to something.
Okay.
a lot of visitors to your poster and to this conference are not from experimental background and even not from computational. They are from theory. They like new results, new people. They do not mind if something is underdeveloped, but their mindset is more theoretical. They understand only equations.
Yes.
And they
Not only.
okay, forget this figure, show me equation. You'll hear it in progress.
And my brain set has not more from that from my wet lab experience to this.
But it's a good training anyway, and again, it's not a big deal. Just sit and really think about it for a while and
Yeah.
figure it out once, and then
It-
you're
it-
done.
Yeah. Once you put me through the ringer, I will always remember, kind of thing.
And actually, pretty much the same comment to Austin, right? Austin, for your methodology as well, right? You also need this equation. You can
Because we both discuss about our rates, and that's if we're going to discuss rates, we want that. Makes sense.
It's kind of common actually. It's very hard to follow the number in these two tables. Why you are not presenting in as a graph this information?
You're talking this table? This table is this what I had before.
Christian, you may answer more aggressively. You can say you're wrong.
Or is
And then
that
tell
already there?
the figure nearby illustrates the table.
And I have said that before.
I think
Is
it's level in the same difference. Armenia's rate.
Now keep explaining.
I have said it before. Is this was all based off of this data right here.
Yeah, then I look on the title actually, then I thought that, oh, maybe it's different, I didn't understand, okay. Then
Yeah.
why you plotted both, table and graph in the both areas?
It's sometimes this is easier to see the a numerical values in my opinion, and then a graphical for some others. But that is just nice to have both in my opinion. But
Your question was why the
Yes.
points do not coincide?
No, actually I thought that it's different graph, because title was different, so.
she's asking
My
why I
question
put
was why
both
it's
a
not
numerical
presenting in the
table and a
graphical.
graph of the same data.
Well, first of all, your tables have 6 lines. Your graph has
3. We could. Yeah. We took small, like we took certain points.
then how you just like then the question is why you
Oh,
it
were
looks
you
like it's a cheating.
manipulating data now?
Why
Yeah.
you just drop some points from your
It's not cheating, it's correlation.
Isn't
Drop
you know, like as experimentalists, it's also very important.
Yes,
you
it's
show
what all
all your
data.
data, right? You
Yeah.
show all your data, and then you
It's our standard practice.
then you hit it with some nice line which is you think should be, and then if some of the points go in exactly or some points really off, it's not a big deal, right?
Yeah. Yes, and if by doing that, I did
Exclude the table, you won't
incorporate
get-
a lot more air into the graphs.
But this is the right way how we represent scientific data. Otherwise, really, it's cheating.
Yeah. Okay.
Because the question is why you drop this point. How you really know that this will follow this kind of trend?
Mhm.
If you take 10 times more points, maybe the trend will be completely different. Right?
Yes.
More questions? Okay, let's end. So please do not forget to submit your written feedback to Christian. And Christian is invited to implement this feedback, right? Just in case, it is not only for our entertainment, but also for.
But now it becomes crucial, right? You have really 1 week. So probably this has to be really your primary kind of, attention.
Okay.
It's taking time.
So, next presenter is Fatima. I'm just trying to make it to fit.
Three-hour time with Aaron yesterday.
Okay, so you can probably focus on different parts and work if you need.
In this research, we have studied electron dynamics along with ground state structure, optical properties of silicon nanowires oriented in different directions, and all of the observables are calculated as a function of wave vector. Here the momentum is conserved. In methodology, so as I said, the momentum is conserved here from for up to this calculation, like this poster, momentum is conserved, but in future I'll calculate when momentum will not conserved. So the non-adiabatic couplings for electron degrees of freedom are obtained from Initio Electrodynamics nuclear trajectories, and those non-adiabatic couplings are used for calculating red field tensor matrix elements from red field equation of motion. And then the red field tensor matrix elements provide the probabilities of transition in different electronic states. And the Redfield tensor matrix elements are using for calculating the electron dynamics. Here we can see the band structure for 3 different nanowires, and as you can see here for this one, the crystal growth along 111 direction, the band gap is indirect. So in order to release photon for electron, it's not possible directly. So electron has to pass different steps, unlike these two nanowires. Then we can see here the density of states calculation for 3 different nanowires. So for silicon 111, we can see the density of states is higher on the conduction band compared to valence band. So we can assume that electrons will relax faster, since density of states is higher in conduction band. It is for silicon 111. For silicon 100, we can say the holes, the density of states for in valence band is higher, and for 211, they are kind of same on both sides, on both band, conduction band and valence band. Here the Redfield tensor, we can see that the transition probabilities, it's always like the same orbital indices or one step plus minus 1 actually. So and we can, as we can see, all the off diagonals, there is no matrix elements, all of them are 0. For electron dynamics, so there is a relation between the density of states and electron dynamics, obviously, since in conduction band the density of states is higher. For silicon 111 nanowire, we can see electrons are relaxing faster than holes. And for crystal growth along 100 direction, we can see kind of same for electron and hole. Here I considered the initial states as the state 4 steps below the HOMO and the 8 states above the LOMO. And electron and holes finally relax at the band edge of conduction band, band edge of valence band and conduction band respectively. For silicon 211 crystal growth, we can see electrons and holes, they are like relaxing at the same time, like at the since the density of states are like pretty same on both as in the here I calculated the rate of transitions. So for silicon 111,
and you can increase, if you do this by 2 fingers, it will come here.
so here all the green dots are for electron and all the brown dots for hole. So for silicon 111, we can see the electron are relaxing faster than hole. So this one, this one, this one. Here, the opposite. The holes are relaxing faster. Now, for silicon 100. For 100, holes are relaxing faster than electron. Since the y-axis is relaxation time, so holes are taking less time than electrons. And for 211 crystal growth, they are kind of same, except this one. So in conclusion, I would say we have studied the silicon nanowires oriented in different directions.
May I interrupt you? Just because you're reading what you wrote already, right? And my question is, this is not really summary of results. You're just saying what you have done, in a sense, in general sense. But what exactly your main results? What we learned from your results?
Actually, we can learn like in which crystal growth direction the electrons.
Then in which?
So for silicon 111, the electrons relaxes always faster.
Okay, this is a result, right?
Yeah.
So depending on the direction of your surface for this nanovirus, you have 1111.
111.
Yeah. This is where electrons are faster.
Yep.
In 100, is it backward?
100, 4 holes are faster than electron.
But I disagree with this, right? Like you're looking on your data, it looks like it's opposite. The green one.
Green ones are
Electrons, right? And oh, so it's time on this side, delta in that side. But just look on your top and bottom, like 111 top and bottom, right? So on your k equals 0, you have red goes kind of, at the top, right? And green's on the bottom. But at k equals 0, 3, 3, it's the reverse. Now green is on the top and red one's on the bottom. Are they switching? Or this is only case when they switch?
Yeah, it looks like here electron holes are faster. This is opposite than other 3K points.
Okay.
Yeah.
So it's, but you think it's probably more like exception rather than a trend.
Yeah.
Okay. But
But
this
I
has to
can
be in the
definitely check
conclusions.
if something is wrong with my calculation.
But this has to be in the conclusions, right? If you really think that there is a trend, right? Then you need just not to say in general that change in a direction of the growth will change the transfer, right? But exactly, at this direction we see this. At that direction, holes are faster. Usually, or whatever. You can put like soften it, right? Say like typically holes are faster. Typically means not always, but in main case. And for 211, the conclusion is kind of the same rate or not?
Yeah, kind of same. No, actually electrons are faster. Yeah, because if we look at the density of.
Let's try this.
And anything else for conclusion? Or this is your main conclusion?
Yeah.
So this is your main thing. Okay.
Okay, then thank you very much. Questions? Any questions are welcome. So please keep asking.
So I'm just wondering what's the reason for choosing the initial acceleration to LUMO +8 and HUMO -4?
I just picked randomly. Like I could pick any other initial states.
Did you analyze absorption spectrum? Didn't you look on the most intense optical transitions?
And are you choosing the energy, right?
For choosing the excitations?
Are you exciting near the gap, far away from the gap? Where exactly are you exciting?
Where do you excite?
Okay.
Does she?
So please focus on it.
Yeah.
But
sure.
do you have this data? You just didn't show it, right?
Yeah, like I don't have space.
Do you have absorption spectrum?
Yeah, I have.
Do you know how to correlate absorption with choice of initial conditions?
I'll think.
Not think, ask. There is someone who can help.
And also, quick question.
I calculated absorption spectra, but I'm not sure. That is
It's
kind of yeah.
presentation on conference is not a paper. Even if something is wrong, you still can correct before you submit it to the journal.
Okay.
So there was a discussion previously when you presented first time. So your density of states, which you're showing, are they already? Is it like density of state at specific K point, or you have some over? So it's
some
total one.
This time.
Okay, but is it now? Do you see a big difference if you have just a density of state at a single point, K point, let's say gamma if it's a direct gap, right? And compare over averaged those. Are you seeing a big difference?
I would say I saw the maximum band gap, like when I calculated separate, then for K point 0.5, the band gap was maximum. Now for overall density of states, I see that band gap is maximum.
But I still think it would be interesting. It's a small technical thing, but would be interesting if you add the dose at the minimum gap. Well, when it's indirect, we cannot do it, but for direct, it's, let's say, gamma point, right? If you just add with a dashed line, and you don't need to color, just dashed line, density of states at gamma point for those where you have direct band gap. And for those where you don't have direct band gap, I don't know, you can also show gamma point just for consistency.
So you said just, I need to calculate the density of states just for gamma point?
You have it, because you had it in
your
your
I have. Yeah.
So just the gamma point, add this as a dashed line to your figure. Like you have already figures there with density of states.
I see.
And just add another line, I would suggest dash line to separate it from your solid line, right?
Okay. Can you please write it down on my poster so that I can remember?
Because again, the question is, are we really losing a lot of features if you look just on a single point, if you use just a single point calculation rather than all average over all K points? And it looks like already that because you have flipping in dynamics for your rates, right? Looks like your K points behave differently, and you really need to include all of them. But for dynamics, it is obvious. But for the dose, I think would be also a good idea to show how much is it different.
More questions? Javed.
If dose is average doses, I'm just wondering that 211 is look like band gap is higher than 11, right? But in this dispersion curve, it seems like 211 is smaller band gap than 11.
211 is the lowest band gap.
211 is the lowest. So in the spacing, it seems like it's long.
So are the x-axis of the density
Is the same range or?
Oh no, the scale is different.
Oh, okay, that's why.
Oh,
Yeah.
So I need to
you
show
need
the scale.
scale, yeah.
Okay.
Fatima, did you ever heard about energy gap law in spectroscopy? Can you relate it to your analysis? Maybe not now, next time.
Yeah. So it is expected linear.
Huh?
It is expected linear
It is expected that the larger energy offset slows down the relaxation. And it is just gives your reference point to see whether this gap law is supported by your data or violated.
So then, in order to do that, I need to fit. So in order to do that, I need to feed the point.
You may fit if you have energy and time. It will look nice if you fit. But some of the data look scattered. Some of them are linear or exponential, and some of them are strange. But analysis of the data.
So suppose for this one, I can. Is it okay if I feed them one exponential and the another one linear?
Would be very interesting.
Well,
Okay.
if you can use. If you can,
And for
I don't see any linear behavior here.
But she has experimental background. She can do wonders. Correlations, as we discussed today. Okay. And you may want to keep organizing it in right now. All data are mixed for nanowires of different direction and for different K points. You may split your point. Right now, your poster is like a table with different columns, but you can also do different rows. Like first row consolidates data for first nanowire.
I have a better idea. What if you just box? Like your first 4 guys, right? It corresponds to the same surface. Just make a border of whatever, red color, right? Then make a border of blue color for the 111, and then black color, whatever your favorite color, for 211. And you can use this color scheme for each case where you're showing each of them. And it's minor contribution or minor changes into your poster which you have right now.
More questions 1? More questions 2? More questions 3? So please don't forget to collect and get the feedback. So for the remaining 25 minutes we have 3 presentations, as it usually happens. Please make some noise. Oh, I was doing noise to check that we are.
Oh, that's the way.
Forward it to Dmitry.Kivin at Gmail.
Who's the next one?
John will do next one, or maybe I already forwarded. Check.
Oh, this one is just a whole electron and hole, because with the time this.
And who is next after John? Are we having?
Yes, we have all.
I'm not sure.
Huh?
It seems
All?
like at the high
What do you mean
energy.
all?
We have all presenters. Everyone is.
So John is the last one.
No, John, London, and Dr. Han.
Ah.
Did you?
It's energy from
So, unless it's still trying to send. So it's
the initial.
Oh, maybe you did send the link, not the
initial acceleration.
Actual file.
Lumo plus A.
Okay, then let's give floor to London.
This is the dissipation.
Now you know what's going on.
This energy is by the time. So that energy
And
is
we'll figure out things with John.
At initial time you can not change energy, right? So it's here. But that's why there are no point zero. Yeah.
It sends through Gmail.
Oh, this one is same, but presenting in a different way. This is the epsilon. This is the way electrocute. Yeah. And then initially is here, and then we average energy is decreasing.
Do not wait, start.
So I am trying to model the electron dynamics at a cesium lead iodide perovskite and spirometad barrier. Let's see, so I guess the way that I'm doing this is I'm only simulating one dimension that travels across the boundary.
With the time,
Um,
changing.
So what I'm doing is I'm starting my electron wave packet as a Gaussian. I'm going to see if I can get this to eigenvalues instead of a Gaussian, because that would probably give me more accurate results, but that's still in the works right now. So essentially what I'm doing is I'm starting it over here. This is time 0, this is like some intermediate time, and this is the end. I'm starting my wave packet in the die, and then giving it some initial momentum, and trying to send it across to the perovskite and seeing how much of that electron density goes across that boundary and how quickly it does. So the way that I'm actually progressing that electron through time is through the evolution operator, and for the Hamiltonian, I'm just discretizing the second derivative. So let's see. And I guess from my initial momentum that I'm starting my electrons with, I'm able to calculate a photon wavelength, assuming that the photon excited the electron in that appropriate direction, using these equations right here. So in my figures, these green lines here represent the potential energy. The red line represents the electron probability distribution at any given point in time. So the red line is not to scale. That's just, it's moved to make it visually appealing. I guess the potential energy is in atomic units. I've also updated this little bit right here. I basically extended the boundaries out because the code runs on periodic boundary conditions. So now what I've done is, instead of having it just set to 0, I just set it to whatever that boundary value is. And that does seem to be changing the results a little bit. I have to get more data to figure out what exactly that's actually doing to it, though. I suppose I should mention that I'm modeling the interface in 2 different regimes. There's a through space regime and a through bond regime. So the through space, you basically just take perovskite and the spiro-omitad and just butt them up together. You don't really do anything fancy with it, and you end up with a wider, higher energy barrier. And then the through bond regime, you use methoxy linker groups to actually chemically bond the perovskite to the die, which results in a narrower, smaller energy gap. So it should result in faster, more probable transmission of the electron. So this data at the moment is outdated, I guess. I'm still working on getting more data to update that. And I'm definitely going to include the transmission rates. I guess I don't even know if this is really relevant to solar cell applications. Am I forgetting anything major?
You think you're done?
Well, I thought I was done last time, and I forgot to mention about half of the things that were going on.
Okay, the front of the audience will remind me. Are you done 1? Are you done 2? Are you done 3? Okay, that's fine. So, presentation is open for discussion. Standard question: main result and main equation. How do you know that it is main equation?
Well, yeah.
Yeah, I guess I'm not really sure what the main equation
Okay,
would necessarily
what is your main result?
At the moment, all I can really say is that qualitatively, the through bond regime yields better electron transmission.
And which numbers supports, or which figure supports this main result?
That would be this figure here.
Okay, this data were collected with help of which equation? Which equation represents these data points?
That would be this equation.
It is x-axis for wavelength.
Yes.
What on the y-length, things that change from 1 to 100, which equation helps you to find it?
Could you repeat the question?
So your blue and orange bubbles, each is encoded with x and y,
Yeah.
2 numbers. For the x number, you have your wave of speed of light divided by frequency.
Right. Yeah.
But for the Y data, which you encode transmission probability, which equation allows you to find transmission probability for one or another system?
It's not really so much of an equation, I guess. So at every different initial momentum that I started the electron with, I can correlate that to a photon wavelength. So that determines the X position, and then I guess you can't really see the other one, but on this graph, I'm just using this plateaued value for the transmission probability. And then what I'm going to do is use the slope of this section here to figure out the transmission rate.
Good. Slope. Plateau of transmission probability.
Yes.
Transmission probability, which letter do you denote it with? Transmission probability, which letter?
TP?
Okay, TP. What is the equation for TP? Which equation determines TP?
How, in other words, how you were able to get your, like you have really number for 5 times, whatever the units, it's equals 0.2, right? Then for time 10, you got something like, I don't know, 0.1, right? So
Yeah.
this curve coming from each point, and this each point was coming from your calculation.
Oh, I see what
But
you're saying. Okay.
which of equation was used for this code to get exactly this data? So you have in your equation for the wave function, right? On the, like your first equation.
But you do not have equation for TP or P. For
Okay.
But then the
Yeah.
question is how your wave function can be used to get the transmission, or whatever you call it, transmission coefficients. Right?
Yeah. So for that, basically the way that it works is I just divide the entire simulation into 2 cells, essentially.
Huh?
It's divided right at the peak of this energy barrier. So what I do is I just sum up the total electron distribution, which should be 1, and then I take this ratio, or sorry, yeah, this number divided by that to give me this ratio.
So you kind of split your wave function into the special part.
You split your space onto 2 regions.
Right, yeah, I'm looking at how much of it is in the die and how much of it is in the perovskite. So this is
And
representing
then
how
take
much of
the
it came to
ratio
the
between this and
perovskite.
that, right?
Yes.
Okay.
Can you do an equation to accompany this description? Like P,
Well, I guess, yeah, like
P
whatever.
equals psi absolute value squared. P like probability.
It would be.
And then integrate it from like 0 to the border.
Right,
Because
yeah.
really,
so
how you explain your red curve is your psi, right?
yes. Well,
Or psi
no,
squared.
not the size.
Psi
It's-
squared,
yeah,
the density,
yes.
right? So psi squared. And then you just really like when you say I sum or integrate, right? So
Right, yeah.
looks like you just really need to
all
integrate,
the
and
way
you
to
need
the
just to
boundary here.
define the range from whatever. And you can put not numbers, you can really put like
Graphically, area under the curve. Fill it and then make arrow. Area under this curve is the probability of transmission.
Okay. Makes sense.
Or for those who are graphically illiterate, you can still put equation. There are many people who are brilliant in equations and not very smart in figures.
But you also have this value for a related question to previous one. So you have this 9.4 angstrom and 6 angstrom kind of the distance which you call through the bond and through the space, right?
Yes.
And when you integrate, like how exactly you know this border and integrate up to like middle of these specific distances which you already point out on the top panel? Like what exactly your border? How you specify your border?
So, okay, so for the border, I
For the
just use
integration.
the peak value of the potential. And then for the width of the barriers, I just went from the trough to the trough.
Oh, so you took in the minimal or whatever, maximum, whatever you call it, of the potential.
Yes.
Which looks like it's aligned with your blue line, right? The right blue line.
I mean, they shifted a little bit, and this is just kind of a quick thing. I mean, this blue line should technically be right at that minimum right there, and this one should be right at that minimum.
Oh, it's kind of in the middle of between this and this. Okay, I see.
Yeah.
Good.
Where did you got your green lines?
From Aaron 40.
By which
What did it?
man with a cap. Aaron. So which equation did he use to get it? If Aaron will be not nearby when you explain your poster. So how do you correlate your atomic models on the top of your central column and green potentials?
I guess I'm not really sure how to answer that question. I kind of have a hard time reading that paper because there's a whole bunch of stuff that I don't really understand.
The paper doesn't show it. It is not explained in the paper.
Oh, okay. That
So
would
you
You
probably
need to
be.
catch Erin and ask him.
Ask him directly. So, but what you have already done, or what is intuitively seen, what is your x-axis position, angstrom, right?
Yes.
And your atomic model on the top of your poster is three-dimensional.
Yes.
So which direction in your atomic model corresponds to your position?
I guess I can call it the z-axis, but that's kind of arbitrary. I mean, in terms of like the way that those are oriented, it would be this dimension.
Okay, so you can label it Z and tell that potentials, three-dimensional potentials, which are minimal near each atom, are integrated over X and Y, converting three-dimensional function into one-dimensional function.
I'm not sure.
You can. You can. We may discuss more, but it is not very complicated.
Okay, but wouldn't that completely change what these are? Because I'm just literally using the z dimension.
It is explanation how these lines were obtained.
Okay.
You don't need to change anything in results. You need just add explanation.
Okay.
Okay? Integration over X and Y of three-dimensional function gives one dimension.
Okay.
There were three dimensions. You integrate 1 and 2 and have 1.
Okay.
Good. More questions to London?
You might have already covered this, but I know we talked about this last time. Which of the many barriers on each of those plots is the main barrier that you're talking about? Maybe it'd be good to show that. I mean, I know you have the two vertical things, so maybe like an initial momentum direction, just so if somebody was just glancing at the first plot.
Oh yeah, just kind of put like an arrow pointing that way.
Or anything to let them know what's happening physically.
Yeah, but yeah, this would be the main barrier to overcome. Just a little, this part here.
If more questions 1, more questions 2, more questions 3. Let's thank London once again. Don't forget to submit him the written copies.
And energy difference at certain time and any time.
Snapshots for your dynamics.
Energy difference
Yes,
of
just to
initial
kind of show the
Maybe
progression.
you need really get some
And
kind of
To actually like
energy
like-
difference
call
at
it with
certain time.
Each previous time you were presenting, system was recording only
And the
your
energy
really like this, I
the
can figure
difference
it
of
out.
these
But
two
Yeah.
people will come to a
is the
post and they
dissipated
will
energy.
ask these
face
questions. So
and slides were not recorded. So in fact, right now, it is the first time.
Simply aware exactly the same.
Right. Yeah. No, I
Or
did
you
like.
can even put like initial.
I don't know if there is a clicker that you can travel.
No, sorry, energy changing, but rate is not changing. Rate is
Okay.
dissipation time is still absent and the same.
So
Yeah, that is how I did it. It's just
Energy
basically
is-
beginning end and
And
then
of
like
course,
right.
constantly
but when you
back
explain
towards
it,
the
it's
anyways,
clear.
so this is
last point here.
mostly to try to collect all my thoughts from last week. I had about 20 slides.
Get your
May I attract your attention to the next presenter?
The whole energy is more than
Okay, so this is a collection of all my thoughts and your thoughts and trying to reduce the information and bring out the most important aspects of what we did in a short amount of time. So I'm going to be talking about the same type of material a couple other speakers have already discussed, talking about methyl lead iodide perovskites. But in this case, we're not looking at any type of interface between dye molecule and a bulk material. Instead, we're going to be looking at what happens when there's a defect inside a bulk material, and also what happens to a material when you spatially confine it into the size of a quantum dot. And so Propagate Materials are obviously a very hot material in photovoltaics and optoelectronics. We're interested in electronic transitions and the many types of molecular motions that may be contributing this. And so if we would zoom in and look as to why, if you look at just here, the yellow field orange circles, those are the data points for photovoltaic efficiency using Propagate Materials, and it's up already over 22%. And that's just in the span of about 9 years. So that's why.
I mean, I can wait up to the end, but I would just immediate suggesting. If you say you increase, really cut,
okay.
push a button, and it will be really going.
I have that in other sections. It just takes the one and zooms it out.
It's very easy.
Okay. Then I'll put the other slide.
Because it's completely unclear
from
this
that.
form.
Okay. And so to try and narrow our thoughts on what we're most interested in with these types of materials, we're looking at the electronic transitions that occur after some type of photoexcitation. So these can be broken into a couple different types. Relaxation mechanisms, which we're specifically interested in, non-radiative, radiative, and also a non-radiative recombination. But we're also interested in the possibility of a multiple exciton generation, which is the ability to produce 2 electrons using 1 photon of high energy, and less specifically charge transfer for this presentation. And so we're interested in these types of transitions that occur, but how are we going to go ahead and explore these? And so we're going to look at the 2 different models using a range of different methods, primarily done in VASP, but looking at spin restricted, looking at multiple K points, looking at spin polarized calculations, and also trying to take into account non-collinear spin, because spin orbit coupling is something that's very important for large metals such as lead that are present in this material. And so from these ground state electronic structures, we want to incorporate the molecular motions that allow these types of relaxations and electronic transitions to occur. And so going through calculations of molecular dynamics, non-adiabatic couplings, we can look at a propagation of a time-dependent density matrix and follow this to find average energies of charge carriers and their effective rates within the material. And so using 3 main types of density functional theory, the primary goal of what we want from these is the resultant energy levels and the Kohn-Sham orbitals that go with it, because the Kohn-Sham orbitals are going to be the basis in the solutions for the remainder of the talk. And so here, just to highlight a few differences between the standard DFT, looking at spin polarized, which is going to provide the energies and Kohn-Sham orbitals in terms of spin projection, but also in non-collinear spin DFT, in which the Kohn-Sham orbitals are are presented in a spinor format. So we're not spin polarized, but still contain components of spin in them. And so these Kohn-Sham orbitals are shown in the spin polarized and the non-collinear as components to the solution of our transition dipole moments, which will be essential for our electronic transitions within the system. And so to account for the molecular motion within the systems and how that relates to the relaxation and transitions, from a ground state trajectory, we're going to find updated atomic coordinates and look at how the wave function is changing from one set of coordinates to another. And so looking at the wave function overlap between these 2 time sets is going to allow us to calculate these non-adiabatic couplings. And so the non-adiabatic couplings can be manipulated and end up providing us with components of a Redfield tensor, which is this R value here, and is used in the dissipative portion in solving the equation of motion for electronic degrees of freedom. And so this solution to a time-dependent density matrix is the key in understanding the rates of non-radiative and radiative relaxation within these materials. And so when we broke the different types of transitions down the relaxation mechanisms are found with the previous slide, but we also use a different type of calculation to look at the multiple exciton generation. And so this is done with the help of a colleague and the co-author in terms of using the Bethe-Salpeter equation to calculate out exciton wave function and energies in terms of looking at this multiple exciton generation effect. And so here, in substitute for the GW equation, he uses DFT with an HSE06 as input for the VSE equation. But then from there, we're going to go ahead and solve for 4 different aspects that make up the total rate for an exciton to a bi-exciton type transition. And so the 4 different types of, the 4 different fragments that go into this rate are the exchange and direct between the particle and hole, and are primarily modified by changing the ordering of the single particles in this screen Coulomb matrix element. So that's a quick look at how we want to take a look at this. And so what are we actually looking at? So for the bulk material with the structural defect, we're looking at this type of bulk methylammonium perovskite material with a lead vacancy right in the middle with the 2D section showing here. But we're also interested in, with removal of a lead, it creates a potential charge deficiency within the material. And so we're going to add in 2 electrons to account for these valence electrons. And by doing so, we're going to create open shell non-spin paired electronic configurations, which will potentially need to be taken into account when looking at the optical properties. And then the second model we're looking at is this quantum dot model, which is just 3 unit cells of cubic phase geometry, stoichiometrically balanced with 6 additional methylammonium ions. And so in looking at the electronic structure of the defect model, we can see from the pure intrinsic system itself, this matches very well with what's been previously reported, with the gamma point being found to not be the direct band gap. But in doing so, and taking the calculations at the gamma point, we need to be aware that there can be large structure changes, electrical properties at other momentum points. And so to take a look at how these different K points can be affected by a type of defect, we did structure calculations with the defect and then a totally corrected, charge-corrected system. And so you can see with the defect, we still maintain the defect state itself, but once we have a charge correction, that defect state disappears. And so in looking at absorption structures, or absorption spectra, which are K-point dependent, on the top you can see the total absorption spectra with this lead vacancy. And so you can see that with this additional unoccupied state, you have a larger absorption onset stretching out further into the red and your infrared because of the reduced energy. And you can find that breaking this down into specific K points, you can see that there's only a handful of K points that are really contributing that far out. Now, when we go back to the standard charge-corrected system, we see an absorption spectra that matches very similar to that of experimentally found spectra with this absorption onset just past 800. Now, in looking at the open shell structures themselves, what happens when we have these electrons that are non-paired, and how does that affect the resulting spectra? So looking at just one single electron added, you can see that for the 2 spin projections, both alpha in red and beta in blue. With this vacancy and 1 additional charge, you can see there's an unoccupied state in the beta. But once you go to a triplet state with 2 spin up electrons, so in this case 2 spin alpha, you can still see this unoccupied state for the beta, but now you have additional charge above the band gap of the system. And so one of the other unique things in taking into account multiple K points is when you're looking at how these states are distributed, just solely at the gamma point, which is the two left figures, versus the total K point mesh on the right. And so what you can see is there's a little bit of the conduction band, the valence band coming back in on the edge, whereas for the triplet, you now no longer see, a specified unoccupied state for the beta system spin projection, but it's now migrated back closer to the valence band itself. And so this pushing of density for the spin projections can greatly affect the rates for different types of relaxation mechanisms within the material. Now I mentioned looking at the system with spin orbit coupling or nonlinear spin DFT because spin orbit coupling is strong. So what we have here are absorption spectra both with DFT plus spin orbit coupling in black versus just the standard DFT. And so for the intrinsic system, you can see that the features are nearly identical. There's just more or less a 1 electron shift in the total energies. But once we start going to a vacancy system and just a one singular spin corrected system, now we start to see this initial shift in most of the intrinsic absorption transitions, but we still maintain these lower energy type transitions, which can signal that when looking at these types of density of states for these beta projections, you're seeing a low energy type of transition. So the spin polarized data can be very helpful in understanding what might be producing these type of transitions signified by the spin orbit coupling calculations. And so once again, once it's spin corrected, the peaks themselves are very similar, but again, just with a shift. And so this, oh shoot, I forgot on an earlier slide, a plug for Fatima's poster. This one, oh, not that one. And this is something in the works, and we're trying to look at non-adiabatic dynamics between multiple K points, and so Fatima will have a poster. And then also on this one, so the next step for this is actually doing the non-adiabatic calculations with spin orbit coupling already in hand. We've gone through, and Dr. Hahn has already applied this to test materials. There's also a poster by Aaron that you may talk to him about this. Okay, so the main results in what we're looking at the different types of relaxation rates within this bulk defect material. So when we look at a pure material, electron relaxation rates are somewhere around 1 picosecond, which is more or less on the same time scale as experimental observations. But the next thing to highlight is as soon as we start looking at the systems which have any type of unoccupied state within the band gap, you start to see these extremely long, upwards, getting close to 100 picoseconds of relaxation time. And so this larger subgap between unoccupied states is going to create this type of extended lifetime. And so with this type of extended lifetime, one might be able to try to collect these types of charge carriers in the material for an increased photovoltage, or if so applied, the longer lifetime of a single charge carrier could be used for some type of redox chemistry. And so in looking at a time integrated emission spectra, you can see that for the main band gap values, you get fairly large peaks for emission, whereas with a separate type of subgap systems that have these unoccupied states, you get larger peaks again for, I guess this would be the true band gap, but also these subgap energies that are coming through. And so in looking at the quantum yields for the different types of materials, you can see that for 3 separate materials that don't contain, or systems that don't contain this unoccupied state, the quantum yield can be very high, which is also in par with what's currently known about the optical properties of the material. So in switching to a comparison of the rates with the quantum dot themselves, the quantum dot portion of the material, from what we found for higher energy photoexcitations, the rates of relaxation and relaxation time follow the trend of energy gap law, which is more or less a linear expectation that the larger the energy, the more time it's going to take. However, once we start getting to lower energy type photoexcitations, the transition mechanisms for these relaxations increased in time. And so one hypothesis for what's directing this is the fact that there could be non-sequential steps for relaxation. So instead of just going through every state available below it, it might jump from one to another, or there could be some type of orbital disconnect, not allowing this type of relaxation mechanism to occur. And so the rates for these are a little bit larger than that of the bulk material, more in the order of 5 to 10 to 20 picoseconds compared to the potential 1 to 5 picoseconds in the bulk material. And so the last portion, in looking at the photoluminescence and the emission of these materials, is that for long-lived charge carrier lifetimes, you can get bright emission up above the band gap of the high initial photoexcitation with the large peak again at the band gap. But with this type of large photoexcitation, we can start looking at the rates of a multiple exciton generation process. And so this green line represents the rate of a single exciton to a biexciton, whereas the blue is a biexciton to a single exciton in the diverse process. But looking at quantities times the band gap value, you can see that the rates for this type of process become very high. And so this type of rate presents itself in about the 10th femtosecond range. And so in conclusion, we wanted to look at multiple different types of electronic transition processes within a bulk material with a defect and also spatially confined, and how do the two different types of environments within methylammonium lead iodide change the rates and the relaxation times. And so within the quantum dot, the multiple exciton generation was much quicker, and because these types of processes compete with one another, the faster it is, the more likely it might be to happen. So by spatially confining it, we're promoting the probability of multiple exciton generation, whereas with this type of defect material, we're creating an environment with a potential trap state to have an extended charge carrier lifetime. So I will stop. Well, I have some acknowledgments for the Killen Research Group. I'll stop and I'll just let you know for now. But
Thank you, John. So, discussion, questions are very welcome.
Can you return back to your last slide?
I have a question to our audience.
This is uncommon.
Who does understand what this abbreviation means after 15 minutes of the talk, which was 20 minutes? It should be 10.
It's different sizes, right?
What are V? Is it vanadium? Or like, what letter V stands for? Huh?
Consensus it's vanadium.
Vacancy. Vacancy. So, but not everyone. I'm done.
your point was made.
More questions? Okay. Again, question about connection between Dr. Fogel and the rest of the audience. On your opinion, who of today's posters and speakers need non-adiabatic coupling, even if it was not mentioned?
Who?
Yes.
Everybody?
Yes. No, everybody. Who wants to ask Dr. Fogel what is non-adiabatic coupling and like, why do I need it?
I'll ask it.
Okay. Well, so if I go back, so non-adiabatic coupling is helping us understand how electron density is going to be transitioning between individual energy states. So when we're looking at the wave function of, say, a specific orbital I and j, we're looking at the overlap between those two. But we're also interested in how it changes with time. So say we have a 1 picosecond trajectory in 1,000 steps. For every step, we calculate the total wave function, which will also give us I and j. At the next time step, I and j, we can look at how they're overlapping and how they're changing from time to time. And so this type of change in the wave function can allow us to calculate what's the probability of electron transitioning from state I to state j or state j to state I. So how do we take into account molecular motion to, I'm not going to say yes, but to calculate the transition probability between those two steps.
Good. More questions? Can you go forward by 2 slides to the? Yes, sure. So, please explain your vanadium.
Also, whatever you think is
and point where the definition is.
But if you think slides were worthless, just cross them out because I obviously need to clean a bunch up. Yeah. So okay. So in our pure material, we're just looking at this methyl ammonium lead iodide structure, which is this MAPDI3. But as soon as we take away one lead atom and create this defect, we have this lead. So if you're reading defect literature, this V is going to stand for vacancy, and the atom that's missing, or the defect itself, is going to be shown below it as a subtext. So the vacancy of without a lead atom, and in this case, because we're looking at the charge correction in the materials, we lost 2 valence electrons, so it's a +2 overall charge in the system. Is the methyl ammonium ion, and then lead N-1. So the vacancy with 1 lead, no charge correction, is N-1. When we go to this lead vacancy now with 1+, we've added an additional electron to the already pure material -1 lead. But because this type of single electron being added to the system creates an open shell system, we also have to identify the spin projection, meaning sigma is either alpha or beta, relating to the red and blue figures I was showing for the density of states. For the bottom, we have a lead vacancy with no pluses, so there's 2 additional electrons being charge corrected, and the sigma value, because now we have 2 additional electrons, they can both be spin up, or they could be paired, or I guess they could be down, but if they're down, they're still projected as up anyways. It's kind of arbitrary for the, but anyway, so this spin number is going to be equal to either a singlet or a triplet. So that's, those are the 4 different models and what they mean. So, question?
Inspired.
Okay.
First.
But then again, back to your conclusion, how is this really affecting your conclusions? Like this presence of vacancies, do you have any observation or whatever?
So on the very, well, I could point to this one. So
no,
this,
I see they're different.
okay. Well, so this table is also on the conclusion slide, but with the addition of these vacancy materials, what's happening is you're now creating some type of defect state that's unoccupied. So even for just the no charge corrected, there's a defect state all the way across every momentum point that was sampled. But once you go to spin projections, you now have this unoccupied defect state in one of the spin projections. And so having this type of unoccupied state means that for some type of total relaxation, you'd have a photoexcited electron, beta electron, and it now needs to somehow take a very large, like singular large energy phonon to assist in this type of relaxation, or you need a multi-phonon type process to account for all this energy that needs to be lost by the electron relaxing. So long story short, defect states.
But can you flip spin due to the phonon?
There, we do not do any type of spin.
You don't, but in general, it's allowed, right? To flip spin
You
due
could
to
do
the phonon interaction.
Yeah, you could do some type of intersystem crossing. Bye, Levi. Bye, Aaron.
Bye, John.
This is what I thought was going to happen last week. That's why I sped up. It was usually 5 to the hour. So intersystem crossing, you go from a singlet to a triplet. So instead of photofluorescence, you get photoluminescence, you get fluorescence. So more of a long-lived process, but that's mostly organics.
Because like you have a very huge difference between your relaxation times if you look on alpha versus beta, right?
Correct.
You go in really orders of magnitude difference,
Right.
from picoseconds to tens of, or hundreds actually picoseconds, right? 70 or something.
Yep.
So which means that probably you, like if you look on your longest scale, it's probably overestimated times because you read, like this is again based on your electronic level, and for beta they're just far away, the energy splitting is far away from this spin fixed states, but if you can flip a spin, right, then it probably following the time of alpha rather than beta, right?
Yeah.
And then overall it looks like you go from without vacancies is 1 picosecond, with vacancies I would say 5-10, in between 5-10.
So I have.
Then it looks like the difference is not as huge anymore.
Right. So okay, so I have a question. So, and I should maybe know the answer, but when you're looking at spin flip type transitions, do you know what order of time they usually occur on? Is it like 10 picoseconds, a single picosecond, or is it material dependent?
Well, if you have spin orbit, it's dictated by spin orbit coupling, right? If it's large, which in LED's supposed to be large, right? This is crossing. You really can
Well, I guess
think
it's
it
not.
that
You
your
can't
coupling,
really say right.
your
I mean,
coupling results on a crossing of your
right.
of your
It's
lifted
components of
sequence or
both
whatever.
alpha and beta at the same time. It's not one to the other. Okay.
So in addition to your phonon coupling, you have this spin orbit coupling, which
Right.
might be significant and
Right, and that's why we looked at least we have it in the absorption spectra, and going forward we need to try and put it into the rest of the non-adiabatic couplings themselves, which Aaron has done.
no, very interesting. But
Yeah.
you should realize there are some
Yeah. No,
some conditions which you really oversimplify.
Yeah. No, I would agree.
So there were two questions from Christian and from Braden.
Mine was purely aesthetic. So if you go back to the other slide.
Aesthetic.
About defect literature.
Yeah, well.
Okay.
So it made sense when you explained it all, but 2 comments. Could you left justify all of them, and then justify the equal signs, and then justify the M's?
Yeah, I could do that.
And then maybe if you could put a little bit more space between each one, it would
Yeah.
make that black blob something readable.
And
Okay.
verbally write V equals vacancy,
Okay.
not
I will-
vanadium.
How about this? I will do what you've asked. I will also put the ends in red with a big bold 1. So, and I will add
Color
V for vacancy.
will help.
Yeah, try to draw the eye.
Okay, so maybe I'm just not getting it, but what's the whole purpose of this whole vacancy model? Yeah.
Yeah, okay, so when I showed this one here, so if.
But is it natural to have a vacancy?
Yes.
Like these crystals have vacancies by themselves?
Yes. So these materials are solution processed. So there's basically a template put down and it's heated up in an oven. And what people have started to do is you have a mixed solution, then they warm it up and they hot cast it. So you pull the hot plate out of the oven, you drop the solution on, and you spin it. And so you get a nice film. But as the material cools, it forms into the crystalline structure itself. But I wish I had our video. We actually made this one time in lab.
You can insert video into
yeah,
slides.
he and I made it. But what happens is you'll see it go from yellow, because it's a lead iodide solution, all of a sudden it'll turn kind of a graphite gray, but you'll see large cracks. So the crystal sizes themselves and the size in which they grow varies, but inside the materials themselves are also defects, because not everything is going to order correctly in this whole process. People are getting good at making large-scale crystals, but defects are always going to probably be present in almost any material we make. So in this case, we're specifically looking at, so this is just the pure material without defect. So you can see there's a wide open band gap at every K point we sampled. But as soon as you take away just one lead atom, you now have an extra state. And so this extra state will modify any type of electronic transition that potentially happens inside the material. So it changes the optical properties, it changes the relaxation times and the extended applications down the road. So,
John, I just want to kind of point one interesting thing, what is happening. You probably can notice when you were, like you were saying all the things already, kind of like mention it when you were presenting, but you probably can see like when you start answering questions, all people are listening to you.
Oh.
You should feel it, right?
It's more comfortable answering questions.
Well, but honestly, like
listen when you answer questions.
people really can now understand you, and they're really interested in what you are saying. When you were presenting, this interest was sparse, right?
Shame on all of you. Then.
So it's shame to us, yes, but it's also showing that the way how you present material, right?
Yeah.
And you probably like really why not? It's probably not really so much about changing the slides, but you can change your story. And again, if vacancy is so important, probably start with the story. Don't start with saying how much perovskites are important and needed. I mean, it's nice thing which you're already showing to us, but you're not talking about really increasing the efficiency for them as a solar cells, right? Probably start with this.
You're telling how to increase it with vacancy.
And you can say, well, this is hot topic, and you really spend a second saying that, well, perovskites are very important because of these applications. And that's it. And then go to the video, explain the importance of your vacancies, because this is what your main results really about the effect of vacancies in this nanocrystals and confinement effect together with vacancies. And if you refocus it, right? So you have only 15 minutes. You cannot say.
Well, you say I've got about
questions. Actually,
11, 12 minutes.
Yeah, but think about it. It looks like you built your presentation on your PhD thesis, right? Which was for 40 or even 1 hour. I don't know how long it took you to present your materials, and it took you 5 years.
Experienced audience can figure it out.
And
without knowing how you work.
And you have 5 years work of collecting all this data, right? And now you're really trying to fit everything in 15 minutes talk, which is really impossible. I mean, you're losing the quality. Putting a lot of quantity, you're losing quality.
Right.
So I would say for 15 minutes talk, really focus on the 1 or 2 things, which really, and you have really interesting story, and when you start answering questions, it's clearly nice and solid story. Just focusing on that. Don't go to everything. You don't have 40 minutes. You cannot make it as a lecture, right? So really just briefly say, well, this important materials for these applications. However, every material has defects, and this one maybe specifically because of the way how you synthesize, how you make them, and yeah, to make it quick again. Of course, it's a lot of defects. And then you immediately go to the focus that this is exactly what you want to look. Confinement in combinations with these vacancies, which you cannot avoid, how exactly they affect the photodynamics, and then go to the maybe say exactly what you mean by photodynamics, right? And then to your theory. Again, probably theory has to be compressed.
Okay. Well, I just say that's why I only had 2 slides with equations on it, or 3. So I can cut it down to 1.
No, that's why it's a good. You need just to maybe, if you're not sure, you may write down each word that you speak and plan it, or just take a couple of shots before, or be eccentric. Like if you see that no one catches about V, you can show periodic table and like ask audience. Do you know what symbol V stands for? They go like, what? He's asking us, and maybe someone very brave will tell, vanadium? No, today is not vanadium. And then the audience will be yours.
Oh yeah, some tricks, because...
Brilliant.
I just had a question, it's probably a trivial question, but can you go to your methodological slide?
Yes.
Your 3 main methods.
This one?
The one that one. Okay. So what's the difference between spin polarized and non-collinear? Is the non-collinear just a generalized version of spin polarized?
So, well, I'll give a quick difference between these two. So with spin restricted, there's spin paired for everything.
Mm-hmm.
For spin polarized, they're still up and down, but now they're just separate.
So spin restricted, you can't have 2 separate states, or triplets.
Well, more or less, correct.
Okay.
I mean, we don't calculate it because you can't isolate it one way. But
I guess that the label spin restricted is not perfect for the first equation.
Should I just delete the first line?
Yes,
Okay.
Yes. What you call spin polarized, some people call it spin unrestricted.
Right.
It's a more common notation. Spin
Restricted. Well, that's why I had spin restricted versus
Yes.
unrestricted.
Spin restricted, you
What
don't
you
really
show
include
is
spin at
can be
all,
called
right?
spin restricted, but
Just
people are indefinite and can be, you can affect their feelings to attachment to some words.
Okay. Okay.
You can use your polarized if you really like it, but I would put in parentheses
Unrestricted. Okay. Well,
unrestricted, or you can say unrestricted in parentheses polarized.
Because like in Gaussian, all
It's a keyword.
keyword
Everyone who is doing
you
spins, they
you
use
through loop, UPB for
Oh,
unrestricted.
doing it that way. Okay. Okay. So yeah, that's kind of the difference between these two. So with spin polarized, there's specific up and there's spin down. So it's plus and minus 1/2. When you go to, I don't know if I can move this. When you go to this non-collinear spin,
And we have
Wow.
one presentation more.
okay. Anyways, just this will be enough. Oh. Okay.
Better?
Sure. Yeah, I was trying to move it. So when now, because your solutions you're looking for them in the Kohn-Sham orbitals, at least that's what we're going to use. So instead of just being still just a singular alpha or beta that's separate from itself, you now have two spin components. So there's no longer a set value of plus minus 1/2. It's now a combination.
So it's a generalized version, kind of.
Well, it's a much more expensive version on how to actually have the correct spin projection, because it's a combination of both wrapped into one. So it's defined as a spinner.
In first method, it spin up or down. Here it can be spin aside.
Yeah.
Okay.
Yeah. So it's not a fixed plus or minus value.
But you're not doing, or you're doing non-collinear.
Well, we show the absorption with the spin orbit coupling
okay.
done.
But dynamics is done just with
Dynamics,
unrestricted.
right, and so that was kind of the point of showing the spin orbit. There's still the low energy transitions with the spin orbit and the spin, so hopefully we can pull something out with the spin. But, okay, now I think I'm done.
More questions? 1, 2, 3. So please don't forget to return handwritten, collected, prepared. And now, last in time, but very not least in importance, presentation by Dr. Han, which is a poster, but it has a lot of interesting information. So, it is one of the few works that focuses on quantum properties of nuclear motion. So some of Christian and Austin were giving details of this motion, and Dr. Han will talk more about this for different systems and with exotic types of systems.
Okay, so the system I'm working on is a hypergolic system. So typically, a hypergolic system consists of a fuel and oxidizer. So usually, hydrogen and hydrogen derivatives can be used as a fuel, while nitrogen dioxide or dinitrogen tetroxide can be used as oxidizers. So when these two components are contact, there will be spontaneous ignition, even at room temperature. There have been many studies on this specific system, but it is found that the activation energy for the very first reaction is pretty high. It's about 0.4 electron volts. So it is unclear why the hypergolic reaction happens at room temperature. So in this study, we are using Initio Electrodynamics to study the chemical reaction of a monomethyl hydrogen with nitrogen dioxide. And in addition, we use wave packet dynamics to better understand the hypergolic reaction. So the problem of Initio Electrodynamics is that it uses the classical path approximation. And so in this approximation, the nuclei are treated classically, while electrons are treated quantum mechanically. So it is not good for cases where hydrogen transfer or proton transfer are expected to play an important role.
So by using the wave packet dynamics, we remove this approximation. So here is our model for AIMD calculations. So this is a geometry. This is optimized geometry. So we have one monomethyl hydrogen molecule, and on the other side we have 8 nitrogen dioxide molecules. And here I show the snapshot at 1 picosecond in AIMD calculations at 2000 Kelvin. We can see here we have the formation of methanol, and also there are also other new species. So I guess I need to talk a little bit more about the AIMD calculations. So basically, at early stages of AIMD trajectory, we only observe 3 sequential steps of hydrogen transfer, like I show here. So we start with monomethyl hydrogen molecule and the nitrogen dioxide. After 3 sequential steps of hydrogen transfer, we end up with this species, methyl group plus 2 nitrogen, and also HONO. So in the following trajectory, we observe much richful events such as the breaking of a carbon-nitrogen bond. So we have other species like the methanol group or the nitrogen gas. I remember last time there was some question about the changes of pressure and the density. So for Japan. So actually, it is not an issue for us because the changing of molecules only happen at the very late stages of AIMD calculations, and our primary interest is just the hydrogen transfer. So which means in the early stages, the number of molecules is fixed.
And number of moles also the same. So there is no abrupt change of number of moles and no abrupt change of pressure.
Okay, this makes sense.
So from AIMD calculations, we can build this energy diagram. So I have 3 energy diagrams corresponding to 3 sequential steps of hydrogen transfer. So the main purpose of this diagram is to build potential energy surface for our following wave packet dynamics calculations. And we also want to find the transition state. So here the transition state is defined as the local maximum in the energy diagram. And the activation energy is just the energy difference between the transition state and the reactant. So for example, for the first hydrogen transfer diagram, for the first hydrogen transfer reaction, the activation energy is about 0.5 electron volts. And we also did the beta charge analysis. And according to our study, we found the hydrogen being transferred is actually a proton instead of a hydrogen radical. And this diagram, we just characterize the number of different fragments involved in the chemical reactions. So here is the wave packet dynamics. And from the energy diagram, by using some technique, we can just build the potential energy surface. So here the energy is plotted as a function of reaction path. And this region is for tunneling. And this is the snapshots for wave packet dynamics. So the red curve corresponding to the initial state, and the green curve corresponding to the final state. So this is for wave packet dynamics at room temperature. And this is a colorful representation. So basically at 220 atomic unit of time, we can see the splitting of the wave packet. So this means some wave packet has converted to products while tunneling, and the others are just reflected back. So from here we can see the about 18% has converted to product. And we also calculate the rate at the different initial conditions, which corresponding to different temperature, and we record them. So here the rate is plotted as a function of temperature,
And then we do some curve fitting using the modified Arrhenius equation so that we can get some parameters. And one of the most important parameters we can get from this fitting is so-called Arrhenius activation energy. And this activation energy should be interpreted as activation energy for tunneling. And actually, from this curve fitting, we found the activation energy for tunneling is pretty small. It's about 0.005 electron volts. So it's way smaller than the activation energy obtained from AIMD calculations. So I guess that's it.
Okay, thank you very much. So what is activation energy before your quantum tunneling and after in units of temperature? Just so that we better understand.
I guess for before tunneling, it should be 7,000 K.
How many?
7,000 K.
Okay,
This one, I guess, is pretty low.
like 100K?
Yeah.
So it is
No, I guess it's 70K.
70K.
Kelvin?
Yes,
Kelvin.
In Kelvin.
in Kelvin, yes, 70K. So 3 orders of magnitude change,
Yeah.
activation energy. So main conclusion,
It's,
tunneling is possible and very important.
yeah, it is responsible for the hyperbolic reaction at room temperature.
I missed the point how you calculate your like how you really calculate the size of your potential to get your tunneling. Because the wider the potential, the slower the tunneling, right? So how are you choosing the width of your potential?
Yeah, actually there is a equation I didn't show here, but basically we just consider two contributions. One is nitrogen-hydrogen distance and hydrogen-oxygen distance. So we assume there is an evolution from reactant to the end product. There is evolution of these two parameters. And these two parameters can be used as the reaction path.
I have a provocative question. If the natural or experimental hyperbolic reaction in the nozzles of rocket engine happens at 300K and can occur up to or down to 70K, why do you do ab initio molecular dynamics at 5000K? Why molecular dynamics is done at so high temperature when on the experiment this reaction starts at much lower temperature?
I guess for AIMD calculations at high temperature, we just want to facilitate the reaction. Otherwise, we need to run very long trajectories, right?
Would the reaction go at all if the ab initio molecular dynamics is classical? So there is a chance that it will not go at all, although you know from the nature that it should go.
Mm-hmm.
So it is only a tool to extract potential energy surface,
Right.
to scan potential energy surface. Okay.
What is the particle density versus real systems with your AIMD?
We need to double check the experimental data.
Does it correspond to like liquid hydrogen and liquid nitric oxide or very dense?
No, right now it's very dense gas.
Very dense gas. So because in the combustion chamber it is pressurized.
Is pressurized in liquid phase or steam?
Well, we do not care about it because we are not engineers. But what we can guess, the liquid fuel is injected into chamber, and it is already preheated inside, and it goes to quick evaporation. But then there will be some pressure.
So I guess my question is, are you sure you're modeling the right density of particles to get the reaction to occur in versus real life?
Can you say that again?
Are you sure you're modeling the right particle density with respect to real life, which is why you might need a higher temperature to get those collisions to occur?
I understand the question, but it's far away from real life, I guess. So, but basically we just want to try to extract the potential energy surface. So I guess it doesn't matter, right?
Okay, so you really just don't care about
Yeah.
the okay.
Yes, we do not care. This case study basically is important plus minus order of magnitude in parameters, because the result is 3 orders of magnitude. So if a slight change in pressure or temperature will not affect the main result that activation energy is 3 orders of magnitude lower. So this you can like close your eyes and randomly shoot anything, you'll get this result anyway.
So 2 small things. The year 2, 3, or year 3.
Aesthetic ones.
The first one is yes. So the 3 reactions you have in the middle column.
Right here?
So I assume the top reaction is the upper left plot.
Yes.
The middle reaction is the upper right.
Yes.
Maybe somehow could connect those.
Yep.
And then at the bottom you have a plot, your beat plot in the middle. Looks like a mass spectrum almost. Middle, bottom right. Yeah. What is that?
It's just count the number of fragments.
So distribution of products.
So that's at the end time, or like a time averaged mass spectrum or something?
This kind of mass spectrum, I would think. You can understand it as a kind of mass spectrum.
So it's accumulating over each time
Yes.
step? Okay.
More questions?
I guess I have a trivial question. In your first figure in the top right, I guess I don't know what reaction path means. So I'm not sure like what's changing. In the right column, the left graph on the top.
This one?
Yeah.
Reaction path? What is it, your question?
Yeah.
What is reaction path?
Yeah, I just don't know like what that is.
Like arbitrary reaction coordinate.
Definition of reaction coordinate. London doesn't understand.
Yeah, I just don't know what's changing on your x-axis there.
But is it the same as reaction coordinate? What? Because he's having path x, which unclear.
So let me translate question of London. What is the difference between these 2 figures? They look similar, but why they have different x-axis? Right?
Sure.
Okay, so here the total energy is plotted as time, but actually for actual potential energy surface, it's energy versus the reaction coordinate. So we cannot get the exact reaction coordinate from AMD calculations. So instead we use approximation. So we believe there is an evolution of bonds from the transition from reactant to end product. And this changes of bonding distance is related to the OH distance and the NH distance.
Okay.
You can think of it as like a space curve bounded on a potential energy surface, going from well 1 to well 2, which is reaction product, going over a hump.
Okay.
So just any arbitrary space curve parameterized by time. Does that make sense?
So we can say that your x here on this figure corresponds to the change in the bond length.
London, should I
between
start
carbon
with,
and
or you
oxygen?
need more?
Well, actually asking the same question.
If the format of poster would allow to zoom in into this figure, one can check those as snapshots of molecular dynamics or cooled molecular dynamics along the reaction path. And what is changing here? What is different in the initial and final? The proton, the hydrogen that originally is attached to nitrogen here, departs from the nitrogen and arrives to oxygen. Departs from blue and arrives to green. So it doesn't go linear, straight line. It goes some like, but in average it departs from nitrogen and approaches oxygen.
Is it really true that your x just corresponds to the change in the distance between n and O, or whatever, n and C, wherever you are measuring? with time, which you're getting from the simulations. Yes?
This is kind of our approximation. So this is the summation. So at each step, we record the distance of OH and
So this is distance between what?
OH.
OH, and this is between NH.
Yes.
Ah, so kind of taking, it's not a specific bond, you taking some kind of two main bonds
Yeah, because this
and
is a
getting
hydrogen
kind of
transfer,
an
right?
average or something.
Yes, this is a hydrogen transfer from nitrogen to oxygen.
It's the same hydrogen in both bonds.
Yeah.
Ah, okay. Oh, it's the same hydrogen.
Yes.
I see. So it's kind of approaching from there to there.
Yes.
Does it help?
I just don't know like the definition of the
But-
reaction path or
Well,
reaction coordinate. I guess
then
like
maybe-
I just don't know what they.
They just kind of make it, right? Well, reaction coordinate is just how you, how the coordinates of your reactant or whatever product, whatever you take, are changing upon the reaction goals.
Like their positions in space. Okay.
Yes.
So then,
But don't forget, you really changing
with
the compound,
this
it's
type
just
of
this change
reaction
in the
pathway,
position.
so
Right.
Because it's not a single ball.
Yeah.
It's really having a real bonds, and if you break
So
this
then
bond,
step
put it
two,
longer, shorter, you're
if
really
anything-
changing the compound overall, right? From molecule A, you get into
This-
molecule B and
so say,
C.
say these are the two the same distances.
Yeah.
But now
So
that's
like.
But technically,
closer
just
to this
changing
one,
the
but total
coordinates
distance,
between some
or are
of
you looking
the
at something where
specific
it's like
bonds.
this,
And the problem is that it's not just a single bond which is
but
changing,
now
but
you
many
have,
of them.
you know, you-
Each of atoms
Like-
starts moving in some way, yeah.
Specifically, the degrees of freedom for any system is like 3.
We went to free discussion.
Yeah.
So the potential energy surface is described by 3 and minus
Square
6
distance.
independent variables.
Uh-huh.
So there's a
Well,
curve.
different ways. You're just trying to put it in a language of normal
Man.
vibration. No,
so
you
It
use
is
it
not
your
that
whole
hard.
basis
Okay,
as the
yeah, I mean,
vibration.
basic
You
distance
can
is
put it extra.
Yes.
Right?
So it is,
That makes
so
sense.
eventually, like, you have
Potential energy
NO2.
surface.
No, I
Like
decided
sliding
to
off
lift
minus
weights
6
for the
and
first
maybe
time in like 4
still
months.
metric.
Yeah.
That's how you get
My
to
legs-
like a
But,
more.
yeah,
So-
his
so-
point is
Oh,
like
okay.
you really go through vibrations, right? Each one
And
having
this is
its
my
own
second group
vibration.
meeting
You
today.
get what's normal mode.
Oh.
Not even vibration, just like XYZ coordinates of each.
You know, what you say
If
is
you want to
get
present
minus
next time, we
six,
can
the
invite
normal
our
Yeah,
modes,
she
vibration.
enjoys
It
your
is,
glory.
yes. Thought process is the same. So then you just have
More questions
yeah.
to the speaker, not to each other.
But it would be a good idea to add this formula or some notification.
It is here.
Where?
It's the top you read it.
You run this screen.
I can see it. Okay.
More questions? 1? More questions? 2? More questions? 3? Let's thank Dr. Khan once again. And please don't forget to submit your written comments. Okay, many thanks to all participants.
What we do for next week?
If you are at your early stage of career, meaning you are in undergraduate studies, you have chance to repeat your poster next time. If you are advanced
And hopefully,
graduate student or postdoc, you probably are good enough.
your poster will have no any empty spots anymore.